Hello, thanks for listening in. It's great to have you with us. You know that theoretical difficulties associated with the classical electron have existed now for about 120 years. They are usually discussed in the final chapters of good books on electrodynamics. Having said that, the purpose of this short video is to give you an idea of how I address the problem from a slightly different point of view. To begin, we need to say a few words about gauge invariance. If we write the potentials formulation of Maxwell's equations for a classical electron, we know the fields follow most simply by applying the Lorentz gauge condition. The resulting point source wave equation has a solution that's given by the Leonard-Weichert potentials. Next, we perform a very special gauge transformation by introducing the scalar field phi is equal to minus e log rho. The foregradient of this function eliminates the Leonard-Weichert potentials and introduces two new potentials which we write as a sub v and a sub a. The form of these potentials is shown here, where r nu is the null vector from the retarded position of the charge to the point where the fields are evaluated. Now there's a good reason for labeling these potentials with the subscripts v and a. This is because in this new gauge, equations for the potentials decouple into independent equations. Of course, these equations can also be written specifically in terms of the field strength, and the price we pay for separate equations is the emergence of a source for current density in the acceleration equation. Everything we need to know about particle accelerations is contained within the acceleration equation. If you quantize the acceleration fields, you get photons, either real or virtual, which can either be emitted or absorbed by an electron. The electromagnetic force is dictated by this equation. But if that's the case, then why do we need velocity Coulomb fields to exert forces on charged particles? In the vacuum gauge, the answer is we don't. But you can't just throw out the velocity equation because it's telling you to do something. Having said that, the rest of this video is dedicated towards reinterpreting the velocity Coulomb fields of a charged particle. Here is the potentials formulation of the velocity equation again. We know that it follows by differentiating the antisymmetric combination of derivatives shown here, but we can get this same result by differentiating the second-rank tensor that I'm calling delta mu nu. It's not a field strength tensor. Instead, it looks like a four-dimensional version of a stress tensor for an elastic solid. For now, let's just say that this other formula requires a new interpretation of the classical velocity fields. Having said that, let's redefine the vacuum gauge potentials by removing a factor of 4 pi times a fundamental surface charge density and writing a new vector u nu. This vector may be referred to as a vacuum dilatation vector. Literally, our vector is a radial displacement of a medium we will call the vacuum out to a small distance r sub e. The overall effect is to create a small spherical hole in the medium with a radius that's equal to the classical electron radius. Now we can perform a divergence operation and determine a scalar quantity representing vacuum dilatation. The parallel with the theory of elastic media is obvious here, so let's continue and define a unitless vacuum strain tensor along with a vacuum stress tensor. The stress tensor is endowed with only one force constant, mu sub e, and this force constant is, not surprisingly, exactly the outward pressure from a spherical surface charge density tending to explode the particle. Now let's write down the well-known Lagrangian from electromagnetism and introduce our new definitions of vacuum stress and strain. After reshuffling, an extraneous term appears with no equations of motion. This leaves a new and equivalent vacuum Lagrangian, and we note that our point charge density has been replaced by a new point source with units of force density. Now we can apply Lagrange's equations in the usual way to determine equations of motion. This set of equations is still Maxwell's equations, except that in this new interpretation, the velocity fields are now momentum flux fields pi sub e and pi sub b, moving at the speed of light. The magnetic flux field still circles around the particle, but the electric flux radiates outward, representing a violation of conservation of energy on a cosmic scale. To be clear, the fields in the red box are nothing more than Maxwell fields, E and B, except multiplied by a fundamental constant with units of surface charge density. The vacuum gauge electron shines like everything else in the universe. According to the stress tensor, which we haven't discussed yet, energy flowing through the Coulomb fields is 1/2 the momentum flux, so it seems reasonable to refer to this energy as vacuum energy. Of course, E cross B momentum still exists, but in the new theory, it's written in terms of electromagnetic flux. Our work also requires a formal definition of the medium, which we call the vacuum, specifically a self-generating deformable medium embedded in Minkowski space-time and characterized by restoring and admissibility constants having equal magnitudes. Great, so now we have a brand new theory of the classical electron, but the next question is this: how do you quantize the velocity fields without creating inconsistencies with quantum electrodynamics? Believe it or not, this is actually very easy to do. For starters, it's important to mention that all the physical quantities defined in the vacuum gauge become elements of a Dirac algebra when operated on by Dirac gamma matrices. In this formula called capital gamma, the vacuum dilatation is a Lorentz scalar, the vacuum gauge potentials are a 4-vector, and 2 forms of vacuum strain result in the antisymmetric field strength tensor. Of course, pseudoscalars and pseudovectors are absent here, so our theory represents a subspace of the Dirac algebra. We also note that while this formula is written in terms of potentials, we can also extract the fundamental surface charge density and write everything in terms of the vacuum dilatation vector. The rest of this discussion is all about finding eigenstates of potentials and field operators defined by capital gamma. Now let's build a quantum theory for the electron velocity fields. Begin by postulating a fundamental vertex or decay mode associated with the simultaneous emission of 2 massless particles with 4 vectors we're calling epsilon sub 1 and epsilon sub 2. Our radiated energy flux is then determined by the high frequency repetition of this vertex. In each of these formulas for emitted quanta, the unit vector hat n is referenced to the instantaneous retarded position of the particle. Both vectors are null vectors and they move along the light cone as shown by the space-time diagram. The invariant energy, E sub vac, is given by this simple formula and has a value of about 140 MeV. The ratio of the invariant Dirac frequency to the invariant radiated frequency is proportional to the fine structure constant. So now we can build a semi-classical theory by defining a number flux density that we're calling n dot. The electromagnetic flux tensor then follows by embedding the radiation 4 vector epsilon sub 1 into a commutator with the 4 velocity of the particle and multiplying through by the number flux. This equation is proportional to the field strength tensor and predicts electric and magnetic flux fields as we've already shown. Now let's find all the eigenstates and the eigenvalues associated with the operator capital gamma. The second term has properties associated with creation and annihilation operators. With these, we can form a number operator and identify a set of 8 eigenstates, 4 eigenstates with eigenvalue +1, and 4 more vacuum states with eigenvalue 0. Both strain operators have the same set of eigenstates, so we need only pick one and find once again a set of 4 excited states with eigenvalue +1 and 4 more vacuum states with eigenvalue 0. This is all the eigenstates associated with gamma. Now let's use a few of them to construct a Dirac spinor. On the right, we show the electron decay mode into directions n and minus n. For this, we can associate 2 potentials vacuum states. Adding these 2 together with the particle mass gives us what appears to be the left-handed component of a Dirac spinor. In a similar way, we can write down a vacuum state of the fields along with its mirror image. Adding these together with the particle mass gives us the right-handed component of the same spinor. Now add these together to construct the full solution to the momentum space Dirac equation. Of course, there are 4 Dirac spinors, but it's easy to construct all of them using vacuum states of potentials and fields along plus and minus n directions. We note that the electron spinors U1 and U2 are only constructed from electron eigenstates, while the same is true for the positron states V1 and V2. Now that we have identified our vacuum states as Dirac spinors, our quantum field theory follows by applying ladder operators to the ground state. We can define our ladder operators beginning with the potentials operators, and then include the time dependence, the Doppler factor, and the fine structure constant. Applying the new operators to left-right portions of spinors propagates radiative eigenstates of the fields. Likewise, applying ladder operators also propagates radiative eigenstates of the potentials. Finally, let's write down the well-known Hamiltonian for a Dirac particle. In our electromagnetic basis, we can write the U1 spinor as the sum of two other functions we're calling psi sub a and psi sub b. These functions shown here are composed of one potential's eigenstate and one field's eigenstate, and you may be surprised to find out that they are both solutions to the Dirac equation with energy eigenvalue E of a Dirac particle. These eigenstates are not pretty, and we don't know if they qualify as spinors, but these two formulas show more details of what they look like. To summarize, we have redeveloped classical electron theory by replacing the Coulomb field with a vacuum radiation field. It works for the classical theory, and it quantizes in a natural way to a Dirac particle. However, a few things have been left out of our discussion. For example, nothing has been said about the impact of vacuum radiation on general relativity and cosmology. Thanks again for listening in. We hope you've enjoyed this short video, and have a great day.